Yeah, okay, let's do this. And this right there is exactly why most PMF company failed to build a good mat in the first place. Welcome to today's video, all about PEMF. This is the big one. The first chapter is going to be about what is PEMF. Our second chapter, we're going to be talking about biology. We need to understand a little bit of biology so we know how PEMF actually interacts with it. So we can understand what makes a good PEMF and what doesn't make a good PEMF. We're going to keep it simple so we can have fun along the way. Now, we're going to finally talk about how much gauze do you really need. But for that to happen, we're also going to have to do some math. That's okay. We'll go through it. Before we dive into this, let's talk about the opening shot and what I showed you guys there. So here we have my simulator running with two magnetic field, and this is where the inverse square law does not apply, and then it's just a preview what's coming up. Okay, so look on the left side, there's 4 coils. Look on the right side, there's 1 coil. The red is the most power, followed by green, followed by blue. I'm going to put a line in the middle of the green zone on the right side of the 1 coil. Look how much bigger the coil is, the EMF of the coil is on the right. This is what we call a destructive field. Quick pause. Uniformity of the field is one of the crucial components for PMF to work properly. If you do not have a constructive field, you do not have a uniform field. Just remember that. We're going to touch on that later on in the video. Now let's quickly look at a constructive field. The one on the left, all the coils are pointing in the same direction. And you can see also the middle line is still in the same place in the middle of the green zone. Now look at the Weber area on the left. Look how much larger it is. Before it was below the yellow line. Now it's way above, right? So this is what we call a constructive field. Many PMF companies don't even care about that. So sometimes you get a destructive field, sometimes a constructive field. You never know what you're getting out of those mats. They don't have a lot of power to start with, and they don't know how to manage it properly. So it's like a big gamble. Let's talk about our first chapter. What is PEMF? Identify the ideal PEMF purposes and what PEMF is and it isn't. That is probably the single most important question for us to go through. So PEMF, is a recognized actual bona fide therapy used to improve health and well-being. Characteristics are very important. We need to understand that. It uses an electromagnetic wave. There's many types of wave out there. We're going to talk about all kinds of wave, and we're going to talk about the most important wave, and I'm going to show you guys a demo of that, and then we're going to simulate the way the human being interacts with the wave. But PMF, what is not, is a healing machine. PEMF does not directly heal you. That is the single most fundamental thing we need to understand. If we understand that, we can figure out, we're going to be one step closer to figuring out how to build a good PEMF. Its applications are very simple, right? It's used in medical and wellness field. Yeah, there are many countries in the world that actually acknowledge the fact that PEMF is an actual bona fide device. Canada has, the United States has, and many countries in Europe have. Look at some of those devices that have been recognized to use. The Canadian healthcare does not pay for them, unfortunately. But if you do have a bone fracture, they like to use some of them if it doesn't heal properly after 6 weeks. So now that we know that PEMF does not directly heal you, PEMF indirectly heals you, we need to understand how the mechanism happened. But before we can go down that rabbit hole, let's talk a little bit about biology first. We're going to compare the human body to a city. A city has many different systems, different parts, different components. So does your body. So we'll just make a big analogy between the two. The power grid. In a city, we have a power grid that supplies electricity to various areas, like in your neighborhood and all over the place. Same thing in your body. Your cell, they need energy to function properly. The mitochondria, which we're going to have a much bigger video coming up soon, they are often compared to the powerhouse of the cell. They're like the power station in the city. PEMF is like optimizing and enhancing the efficiencies of this power grid by promoting a better cellular energy production. It basically, through the power of induction, gives your cell some free energy. The traffic control. In your city, you have streets, traffic lights, you have pavement, and all that, it ensures a good, smooth transition of the goods and the people. In your body, we have the same thing. It's called a circulatory system. It includes your blood vessels. It plays a crucial role in transporting oxygen, nutrients, and the waste product. PEMF therapy can be seen as a way to improve all that. And how it does it? Well, when the EMF pulses, it rebalances your immune system, first of all, which sends a signal to reduce inflammation, which is one of the biggest problems the human body has. By reducing inflammation, the micro muscles around your vein and capillaries get to be relaxed, allowing the vein and capillaries to expand more because they're not bound so tight anymore. This in returns allow a bigger flow, or a flow period, of blood to and from a different part of your body, which can feed your cells. Now that we have a better idea about the way the EMF interact with the cell, I mean, at the end of the day, guys, it's very quote-unquote magical. Remember, magic is science we don't fully understand. So what's happening is it reduces inflammation, which allow your blood to flow everywhere. It also optimizes your immune system by making everything work better. And through induction, it allows your cell to get some quote-unquote free energy so they can go to work harder. So you don't get tired as quickly, basically. So you recover faster. And also, through the use of the PEMF installed in my mat, like the way we build it with the coils and the pillow, and by selecting specific frequencies, we can do a brainwave entrainment, which allows us, like I said in some other videos, to manipulate some of the system that's in the big house. Finally, the moment we've all been waiting for. How much gauze do you need? And what happens if you got more gauze? What happens if you don't have enough gauze? And then we're going to talk about the inverse square law, and then we're going to talk about a bunch of stuff. But I got to warn you, okay? It's going to get pretty heavy really quick. But we're going to make it fun, and we're going to make it simple. All right, first things first, let's look at what's naturally happening around us. Now, this is a map of the Earth magnetic field. What I'm going to do is add a little scale to the bottom there so we can find a relationship. Okay, now we're going to move this to the calculator, the famous calculator. Okay, let's use our calculator. There's a part of the calculator I don't personally use very often, but it's useful when it's there. And it's got the standard prefixes. So in this case, we're in nanotesla. So we're going to convert gauze, nanotesla to gauze. So we pick the N for nanotesla. The lowest parts of the scale is 15,000, and 15,000 is 0.15 of a gauze, which I put right there. Then right dead center, you take the average of 15 and 70. So then the center of it is 4250, which gives us 0.45 of a gauze, right dead center in the green, number 5. And then right around the 7.5 mark, which is a lot of countries are into, what you do is we just make so 7.5. So we know that 10 right up here is equal to 70,000. So we want to know what 7.5 is. So it's just a crossover ratio. So 7.5 times this divided by that gives us this number right here. So, and then we know if we enter that, 52,500, it's 0.5 of a Gauss right there. And then the maximum is 0.7. So the scale is between 0.15 of a Gauss to 0.7, where most countries are at 0.5 of a Gauss. So here we are, back on our map. And as you can see, most places always hover between 0.4 of a Gauss and 0.5 of a Gauss. That seems to be the majority of it. Unless you live south of the equator, basically, then you're a little lower on that. So that's where life evolved on the planet, and this is what we have right now as part of the magnetic field. Earth magnetic field, 0.5 of a Gauss. Check. So let's first talk about what the inverse square law is and it isn't. To be able to use the inverse square law, you need a point source and you need a uniform field. And if you have that, then the inverse square law can be observed properly and measured in that way. And then it's really well known for the filming people pictures and stuff like that, as the light intensity coming from a point source reduce itself by the square of the inverse square of the distance. And that's why it's such an important rule to know. But it does not apply to magnetic field. Why? Because we use the inverse square law when we have a point source. The sun is a good example of that. It is a point source. It also gives us a really uniform field. It's also a distance point source, because the math is a lot simpler and it gives us a really good approximation. On the other hand, we use the Biot-Savart law for extended sources. What does that mean? Like a wire, a cable, a chip, something that's not like a single point. A magnet and an EMF is never a point source. When we need it to be precise, when we really want to know what's going on, and also when the field is near and small. When PMF, we deal with small, near field, basically. All right, Mr. P, you're making me do something I didn't want to do. Let's go. There it is. Which one? It's a really old file. This basically is the file that I use when I design the mat, the coils. Yeah. Okay, so I'm going to show you guys why the inverse square law is the wrong law altogether. I'm going to show you why I did the mat the way I did and the output that we get. But first, maybe we should start at the beginning before this makes all sense. Okay, this is the formula. Don't worry, we're not going to use it. But you see the R and the pi? Well, that's pretty similar to a coil, isn't it? You don't see that in the inverse square law. Now we're going to simplify this formula. And by the way, a friend of mine did that for me because this thing is like things of nightmares. So the beauty in this formula now is that we have everything we need to calculate the magnetic field of our coil. We have the radius of it. We have the number of turns. We have how much current we're going to pump through it. And obviously they're free space, so that one is a constant. But that's what I've entered into my Excel spreadsheet. And then, like I said, it is things of nightmare with the vectors and yeah. So my friend helped me quite a bit. And then from there, we added the Z-axis so we can get elevation away from the coil. We entered all that into an Excel spreadsheet. And then from there, I was able to run simulation, basically. Do this quickly so I don't blow my mind or yours. The 50 mil is the initial radius that I was going for my coil. So it would have been like 100 mil diameter. I know I always talk about 95 mil diameter. That's because my propane bottle is 95 mil, and this is what I got for. it's close enough, so I decided to go with that. Z is the distance from center above the coil right here. And then I did two simulations, one with initial of 50 gauss and one initial of 50 gauss. So if we compare the 50 gauss at 1 mil, and then we're going to compare it to the inverse square law. So both of them numbers will be the same because that's where you start. At 2 mil, if you notice, we're barely going down. And it's going down really slow compared to the inverse square law, which goes down really quickly. And then we really, like when you reach the 32 and the 64 mil, then you really start to drop. At 120 mil, you drop quite a bit. And at 256 mils, which is 10 inches, you drop to 0.7 of a gauss. So as you can see, the Biot-Savart law shows us that the decay of the field is much slower than the inverse square law. We're a lot more accurate. I mean, at 5 inch, we're still making almost 5 gauss, while here we're making 0.006 of a gauss. And I know there's a lot of people with high voltage and high gauss machine, they like to throw that in people's face, but they're using the wrong math. Not only that, because we have a constructive field, we actually gain an extra 40% on top of that because of the way we build stuff. And we're going to talk about the Weber after. So all of a sudden, at a distance of 25 centimeters away from the center, if we start with 100, like 50 gauss, we're still making 0.5 of a gauss. And at 100 gauss start, we're still making 0.994 of a gauss. Why aren't they exactly half and double of each other? I don't know. Somewhere along the line in my math, things went weird. Inserted a quick pause here. Do you see the target number that we're looking at according to the paper I read? Just keep that in mind because it's got to come back in a second or two. But it's close enough for what we're doing, guys. I mean, we're not trying to launch a rocket onto space here. So, just to show that the Biot-Savart law tells us that at 25 centimeters away from the center of the coil, with one coil, we still have this much gauss happening on top, guys. Let me quickly show you guys visually where I get that 40% constructive design. We have one coil on our mat, and it's doing its thing. And we're going to add another coil. Look how we push the line. Look how the magnetic lines get pushed. So if I take it off, look how far apart they are, and all they want to do is come back from south to north. If I add another coil, and I put it in a constructive way, meaning facing the right way, the same way, the right distance apart, we straighten the line. So I push the other lines up. See, now the lines, what we're doing is we're basically shunting our magnetic field in a positive way, in a constructive way for what we need. Because what we need is a big Weber. And Weber, imagine a straight line coming straight down here. And that line, it's like your mat basically, your body. It's how many magnetic flux lines are crossing it. So if I add another coil, there we go. Look how many more flux lines are crossing it. And another one. Whoops. It won't let me go any lower. Let's move this one up. This one over there. This one over there. Look how beautiful that is now. Now, if I grab one of them coils and I put it upside down the wrong way, do you see what just happened to it? Look at the magnetic lines. Nice and smooth, constructive. And here we have a destructive magnetic. We're shunting this in a negative way. Remember, it's always about manipulating the magnetic field. That's what it's about, right? So let's put it back the other way. Now look at the Weber of this, right? How many lines are crossing a plane, okay? Now, let's take a magnet that's twice as strong. So let's say this is like twice as many gauss as the other magnet, right? You're still going to have a few lines because you only have one. If you add, then you got a bigger Weber. It's all about the Weber, guys. It's not about the gauss. You know, part of the formula for the Weber, gauss is included in it. Okay, so Weber is a much better representation. Look how many more lines are crossing. Look how many more lines are crossing. That's what Weber is about. How many lines of magnetic flux are crossing? I hope this helps a little bit. Let's now talk about the magnetic slew rate. The magnetic slew rate is the speed at which the magnetic wave rises and falls. It is measured in millitesla per meter per millisecond. The research paper uses that all the time, and the industry likes to muck the water with this. And then I'm going to tell you the biggest secret that nobody knows and the reason why. So one night I was working in my lab, and then I just got a brilliant idea as I was doing some reading. Instead of using this complicated denotation for the slew rate, what about we use a different one? That made me feel really smart, actually. Not that I invented anything, but that I was able to figure something out to help us. So the slew rate, what about we do a change in the magnetic field, and then the change over time? That would give us Gauss per second. And I thought it was brilliant, and it turns out that it exists already. But now we'll be able to compare apple to apple between all the devices. I love it. So now I'll be asking, but Steve, why do I care about the slew rate and how fast it is? Well, let me explain it to you, and you'll see how it's going to change your mind. So after NASA published their paper, other researchers looking at it, they found out that one of the key parameters was the slew rate, and nobody ever really noticed that. So that made a lot of wave in the industry. Also, that's the same paper that I don't think too many companies read or dare to read. The same paper that says that 10 to 200 milligauss is all you need. That's 0.01 gauss. That's pretty weak field, guys. So like I said, when they realized that the slew rate was affecting the PEMF efficiencies so much, they started doing some more research on it. And this is one of the results right there. And this is where I found out about the Gauss per second, and that really piqued my curiosity because I was never taught that anywhere in any of my books or any school work that I've done. But anyway, they started to talk about different waveform, different this, different that, and then they found that only rapidly changing magnetic field had effect on the cell culture. So that was a big change. So let's do a quick recap of everything we've learned so far. We've learned what the PEMF is and it isn't. We've got a touch on biology. We have a better understanding of the gauze that we really need according to all the research we've talked about. And we also are learning about what makes a good PEMF. So we really started to talk about the slew rate. So let me dive a little deeper into the slew rate so we can really come back to how much gauze you really need after that, and then we're going to close in on this topic once and for all. So now we got the XY axis, and we're going to draw on this the magnetic slew rate of a sine wave. So there it is. Now next, we're going to draw the magnetic slew rate of a square wave. There it is. You can see they both have the same peak. The square wave reached a peak much faster than the sine wave, stays on top for a while. Now here we have a 0.1 milliseconds time zone. I want you to bear with me because this is just a quick presentation, and the magnetic slew rate in red is not in real life looking like this, but I'll show you this in a second. Okay, in this yellow area, that's the only time your cell can actually absorb some of the magnetic field. So in the case of the red one, the square wave, and in this example we got 100 gauss on top, our cell can absorb all of the 100 gauss. On the other end, the sine wave, the slew rate is not fast enough, and in this case you're getting less than half. We just use that as an example, like 40 gauss. So you can see where this is going. Now I made a PEMF using a sine wave, and the blue line is the sine wave that I'm pumping through the coil. The yellow line is the magnetic slew rate of the sine wave. Now I took a measurement to measure from peak to peak, and you're looking at 8.2 milliseconds for the magnetic slew rate to reach from dead stop to dead, from start to finish. So same thing here. I did that with the square wave. The blue line is the output of the square wave, and the yellow line is the magnetic slew rate of the square wave. And as you can see, it goes straight up, followed by a sharp decline to 0, and then straight down, and then a sharp decline back to 0. Let me explain to you a little bit of what's going on here. It's not exactly what's happening, but it's pretty close, okay? Imagine this is your cell, and we're going to use Faraday's law of electromagnetism, obviously. And this is our coil pulsing. When you have a fast pulse, and if we use the biphasic, the bipolar thing, it's pretty much what's happening. It just happens a lot faster than this. So you can see we're inducing a current in the wire that goes up and down, which every time it changes, it lights up the bulb. So this is your cell. This is a cell membrane, the ATP, the mitochondria, and then we're inducing a current. When you have AC, it's a lot slower, and as you can see, this is what's happening basically. It's kind of painful to watch, isn't it? In this case, there is a little bit of energy that goes up, right? But not as much as when you go fast, on the fast slew rate changing. See, like the magnetic field, you see it changing really fast. That's literally what's happening on a mat with a square wave, and that's literally what's happening on a mat with the triangular wave, the reverse sawtooth, the sawtooth, and the sine wave. They all have different speed, but none of them are as quick as the square wave. Okay, let's measure our square wave. We're going to need to zoom in to go from 2 millisecond to 800 nanosecond scale. And then what I did here is I measured it up, and the rise of our square wave is 0.04 milliseconds. So that gives us an idea of the speed at which the square wave rises, because nothing is instantaneous, guys. If you zoom deep enough, you'll find the speed of it. So 0.04 milliseconds. Okay, time for a little quick recap. The Earth magnetic field at 5 Gauss, yeah, we got that. The inverse square law is wrong, yes, we also understand that. The Biot-Savart law is right, yeah, we've proven that. The good field, yeah, we're going to keep that on the board, so is the slew rate, we totally get that. Now, a square wave is the only one that can use 100% of the time. We want to add that up. And the ability to adjust frequencies from unipolar, bipolar, linked, and unlinked. I'll talk about that in more detail another day, but another video. But there's a lot to know about that too. This is the kind of video my Patreons usually get. So we've done a lot of learning today, like a lot. And I'm really sorry if I hurted your brain, but you needed to know this. So how do we build a good mat? Well, really, it's not that complicated. You have a crazy Frenchman like me in his basement that does all kinds of weird tests with all kinds of bits and pieces of stuff. Does a little bit of research. Learn how to use an oscilloscope properly so he doesn't fry it a couple times or sparks it. Then we do a lot of reading. There's a lot of information out there if you know where to get it. There's a lot of really smart people that paved the road for us to build stuff. We live in a world where we have access to so much stuff now. We can do lots of really good stuff at home. Homemade. Got that on YouTube, by the way. Okay, so how do we make a good mat? Well, starts with the design of the Nexium. This bad boy is bulletproof. It's giving us all kinds of stuff that we can do with it, and it's just amazing. It does the most amazing, wonderful square wave there is. The precision of it is incredible. I love the case that I put it in, and I love the H bridge that I use inside. We got the plug-in, and this is rocket. This is awesome. Okay, then we need a harness to hold onto our coil so we can lay on it. I open my mat up this way, and then I put my coils inside and I tape them to this position right there. And then I have this construction zipper that I close the whole thing with. So if I have to do some maintenance, it's easy to access it. Then we build coils. We build coils at a specific size. Remember, I told, like, we went through that already, right? So now you know why I build stuff the way I do. You gotta appease the Ohm's law God, or they're gonna strike you. Then we make our coils on the mat, doing the pillow, one row there. Okay, we spread them this way. The power supply that I use, I can add another row of 5. The idea, guys, when you parallel stuff, you try to make them so they have all the same resistance, or the Ohm's law is going to do some funky stuff for you again. Okay? Just wanted to insert a quick pause here. When you parallel things, if you don't have the exact same load or resistance in each line, it will be insane what's gonna happen to you. The math in this is like freaking really complicated, and the result you're gonna get is not even near what you think. Logic goes out the window sometimes. All right? In the electrical world, when we parallel conductor, the law states that they have to be the exact same length, the same type, and the same resistance. Okay, there's a reason for that. Don't mess that one up. Then, what you gotta do, and this is really, 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 really important, you gotta make them all point the same way. You have to. There's no way around that, or you're not gonna have a constructive field. So after that, you place your coils. Now, you're gonna ask me, I've never talked to anybody about this, my Patreons. I've made some special mat for some special people for really specific purposes. And I made it with 15 coils, 15 big coils. And the power supply can take it. Everything is good there. All pointing the same way. Now, the numbers I'm going to put on the screen for us right now, they're not counting that extra row of 5 right there. They're just the typical 10 coil mat. The 2 and the pillows for the T-PEMF. This is my Porter's Man's T-PEMF. And we're gonna have many videos on that too. And then the rest of the coils right here are for the rest of the body. Now, let's look at numbers. Let's start by talking about the other people. First of all, you only have, like most of them, between 4 and 6 coils, quite a bit smaller. They're all using sine wave, and most of them are between 1 to 4 or 5 gauss. That's usually what you get. Assuming that they build the coils properly, this is kind of what you're getting out of the deal. It's not overly impressive, but don't get me wrong, I'm pretty sure it does something to you. Like, you know, after all, the beamer is what made me start this journey. So I did feel a little bit better after I used the mat. So let's look at the numbers. This is based on square wave, which we know they're not, but we're just going to give them the benefit of the doubt. They're making 0.28 Weber at 2 gauss per side. And the slew rate would be 50 gauss per second. Let's compare this to the mat that I teach people how to build and I build myself. Now I want to open up a bracket first. It's an old catchphrase that said, show me the intent and I will show you the end results. My intent has always been to teach, to debunk, and to find the best way to build a PEMF. So the end result should be that my direction, anyway, is that I will build the best PEMF there is out there. That puts us, you and me, in a very unique position where our initial intent is not about making money. Therefore, we can do things that very few people can. Now let's compare the beamer-like mat to ours. Look at the change. Like when the field is helping each other, the coils are close enough that they're actually doing something that is worthwhile, and we have a giant bubble. But what does that mean to the numbers? Well, you're going to be pretty astonished with what we're getting. Remember, I built this mat with the latest technology, the latest knowledge. We have an outstanding 35 Weber per side. I think it's pretty good, and our slew rate is an astonishing 2.5 million gauss per second. Remember guys, that's the number that gives us how much energy is transferred to the cell. So now you're gonna say, but Steve, what about the high voltage stuff? Well, if that was so good, that's what I'd be using. Now let's go over it. This is a big loop, 5000 gauss. I ran this through my simulator, and as you can see, the magnetic field sticks around the coil itself. It does not make it through the coil. All the magnetic flux lines are totally concentrated inside, and so what you're getting is basically this. You got a pulsing field, but yeah, you don't have a uniform field. Now what does that mean for numbers? Well, look at this. First of all, we're going to go 5000 gauss in a square meter, put a big old coil in the center of it, 0.35 Weber. Yeah, I had to do the math a bunch of time. And the slew rate is 151,515 gauss per second. Now for the purists, I did use this formula for that, and I'm well aware of the 5-time period of capacitors. And I'm going to let them have the benefit of the doubt that they use the proper equipment to measure the Gauss output, which I'm pretty sure they didn't. So okay, my rant is over. But it is a can of worm that I don't want to open up right now because A, I don't have the tools to measure it, and 2, we're probably splitting decimal points at the end of the day anyway when you take all the factors in. Next, let's compare everything we found so far. Now this way of comparing stuff, we can now compare apple to apple. It's not about how much Gauss you're making, it's how much Weber you do. And it's not just about how much Weber you do, it's all the delivery of that Weber is, which is Gauss per second, which is a true representation of how much energy can be transferred back and forth into your body. A higher slew rate means better tissue penetration, better energy dissipation, better absorption by your body. A bigger Weber means bigger part of your body can be exposed to that field. So you can see the industry is somewhat delusional when they're explaining their stuff. I believe one of the major reasons why this is happening is because there's three main factors in PMF. There's the biologies, there's also a big physics involvement in that, and there's finally a big medical thing. And anybody with a PhD in any of those three categories, they think they're the messiah of the PMF industry. I see this all the time where they do not take in account the other part of this triangle. And this is where we get ourselves in trouble. Now just imagine what the world would be like if people like this would actually work together. Look at this fantastic collection of knowledge you just acquired today. I congratulate you. I'm really proud that you are putting yourself and your health first. People like you are needed to debunk this fantastic industry that is the PEMF. It can help so many people, but there's so much snake in the grass out there. So many pseudo experts telling all kinds of junk out there too. Now you're armed to understand more. Now I'm gonna let you go. Whoa, whoa, whoa. You owe me a secret. So I guess I do owe you a big secret. And I hope that by now this will resonate with you guys quite clearly. What you need is a stupidly high gauss per second, so the energy can be rapidly transferred from the mat to your body. 2, stupidly high Weber. Like you need the area covered, not just a small area, the whole thing. Your body works as a unit. You have to fix the whole body, not just one area. I'm not saying that having a PMF application on a direct spot cannot help. I've found over the years that when I get really hurt bad on my shoulder, for example, that helps. Now, how much gauze? As you notice, 0.5 of a gauze is all you need to activate the cell. It's actually lower than that, but I like to keep it around 0.5 of a gauze. That doesn't mean the mat has to be 0.5 of a gauze. That means because of the Biot-Savart law that what we talked about, we need to make 0.5 of a gauze about this high off the mat. So that way you have everything covered. There's also having all your coils put the right way together, so you get an extra 40% oomph on top of that because you are manipulating the magnetic field in such a way that you're getting an increase. So you get the Biot-Savart law, now the inverse square law. You make your coil in a constructive way. You get 0.5 of a gauze above your tummy, and then you got it set. It's not much of a secret by now. I think by now you guys should have got this whole thing put back together, but good job. You're ready to take on the world. You're ready to start your journey with PEMF, or continue your journey with PEMF, or whatever your journey with PEMF is. And I hope this video was fun to watch. I really enjoyed making it. It really made me review a lot of the knowledge I had, really polish on some stuff. But I really enjoy sharing this. This is really what I want to do. This is really who I am. So I hope you enjoyed it. It was something else to make this video. Be safe.
Oh girl, it must be you again. You have gone straight to my head. Take the pills and go to bed, but I'm still hooked on this. Well, you are sacred in a way. I don't know God, but still have faith that He will manifest some way when I am next to you. said. The thought of you in a white dress, I don't think I can shake it. We'll get a little place upstate, stay till the kids all graduate. Talk of moving every day, but who are we kidding?
Oh my god, that was wild.
We made all our memories here, felt our joys and shed our tears. And when the Holy Ghost appears, hope he sends me back a few more years. I'll be buried next to you, the world will keep on turning to. But if I am next to you, I do not care. I do not care.
The math we do gives us 2.5 million Gauss per second and 35 Webers. Your typical beamer mat out there gives you 0.028 Webers and 50 Gauss per second. And the high voltage stuff gives you 0.35 Webers and 151,000 Gauss per second. And now you know why I build a mat the way I do. Isn't that amazing? A little science goes a long way.